let's now turn to the second building block, which addresses how we actually compute the portfolio risk. So let's think of the most simple portfolio that we can have, just two bonds. The first bond is the same as we had before, and now we have a second bond which is A-rated, 5% coupons, 3-year to maturity. Okay, so let's start by computing the portfolio values. So basically what we now have, since we have two bonds, is not just 8 states like we had for one bond, but now we have 8 times 8 states, 64 states. So we have all these possible states that you see here. So how does this come from? The first bond that we had, the BBB bond, can have all these values according to the terminal rating. Okay. Now we have this new bond, number 2, which is single A, and again it can go into 8 possible states, and in each state it will have a different value. So how do we get these values? Exactly in the same way as we did before. So for example, let's check the value in cell AA. Cell AA is this one here. So what does that mean? It means the case where the first bond that is BBB goes to A at the end of the year, and the second bond, which is A, remains in A. Okay, so let's see how we get this number 214.96. Let me show you an image. So the first bond we already did. It's this one here. We got this value before. Now the second bond, the scenario is that it remains A, so it's A now and it will be A 1 year from now, meaning that the value that it will have at the end of the year, it's just the present value of the cash flows, 105, at the forward rates for the A rating, which are the same as we used before in the previous example. So 5% plus 5% is counted at 372, plus 5% is counted at 432 for 2 years. That gives us a value for the second bond of 106.3. So the value in cell AA is just the sum of these two numbers. So it's this one plus this one, 214.94. Okay. So the other values are obtained in a similar way, and each one will be just the sum of the value you see here in this row, in this column, with the value you see here in this row. Okay, so now we have to find the probabilities of observing those 64 states. So the first approach would be very naive, would just be to assume that the migrations are independent of each other. Okay. So in that case, the calculations would be very simple. The joint probability, so for example, the joint probability of the first bond remaining BBB and the second bond now jumping from A to BBB would be equal to the product of the marginal probabilities, right? So I could get these probabilities directly from the transition matrix for each one, multiply the two numbers, and get the joint probability, all right? And this will be the outcome. I mean, it would be very easy to do, but obviously it's not a good approach because we know that credit migration is not independent. There is correlation in credit migration. So how are we going to impose correlation? Again, we cannot look at historical data because there is not that much data on defaults. In particular, if a firm has already defaulted, then the firm is not alive. Okay. For the firms that are alive and that I have in the portfolio, there is not information on defaults. So the historical approach does not work. So that's where this model comes in and solves the issue. So what Creditmetrics does is to extend Merton's model to impose correlations. So the approach is the following. What we're basically going to do is to use Merton's model in reverse. So if you recall, in Merton's model, we had some underlying economic structure, and we would have default when the value of the assets was very low. So below some critical value, then we would get default, and the model would output the default probability, this tail here. What we're going to do now is, in reverse, we're going to look at the transition matrix. We're going to get the probabilities not only of default but also of transition to other ratings, and we're going to find the thresholds that match those probabilities. So this is easy to do with a figure. Let me open this figure. Not this one, sorry. This one. So what we're going to do is the following. Again, I'm going to look at the transition matrix for a firm that is triple B in the beginning. So I'm going to look at that triple B row. And if you go back to the matrix, you would find that the default probability for that triple B firm is 0.18%. So what I'm going to say is I'm going to start with that, and I'm going to say that this is the tail of the distribution, and I want to find what is the critical value that matches that tail. So I'm going to look at the normal table, and I'm going to find in the normal table what is this value that gives me a mass of 0.18%. Okay, and this is going to be the critical value for default, meaning if the return on the assets ends up being to the left of this, so smaller than this, I'm going to say that the firm will be in default. Then I'm going to take the next cell in the transition matrix, and the probability that you see there, 0.12%, is the probability that the firm transitions from triple B to triple C, okay, which corresponds to this part here of the curve. So now I'm going to do what? I'm going to add these two numbers, 0.3%, and I'm going to look in the normal table and see what is the critical value to the left of which there is a mass of 0.3%. And that value is minus 275%. So meaning what? If the return on the assets ends up being between these two numbers, I'm going to say that the firm is or becomes a triple C rated firm. And so on. I keep adding these probabilities and determining the thresholds, okay, until the end. So, and I get a series of thresholds for the value for the standardized return on the assets. Okay. Oops, sorry, not this one. Okay, so you have the procedure here again. You can look at this in more detail here. So basically what we looked at was this part here of the table for the triple B rated firm, which has these thresholds that we just saw. Okay, and I can do the similar type of calculation with the other bonds. So for the second bond, the A-rated bond, I would go to the transition matrix and get these probabilities, and then I would find the thresholds that correspond to those probabilities, right? Okay, the next step is to estimate the correlation between the two firms. Again, the assets are not observable, so what Credit Matrix does instead is to substitute that with correlation between equity returns. The next assumption is to assume that returns follow a bivariate normal distribution. So with that, we can estimate the probability of each one of the 64 states. For example, the probability that both bonds remain in the current rating, so that the firm A remains A and the firm B remains B, is the probability that we observe a return for firm A that is between the thresholds that keep it in A, and for firm B, a return that is between the thresholds that keep it in triple B. So for example, for the triple B would be these thresholds here that keep the firm with a triple B rating. So the joint probability is given by this double integral of the bivariate normal density. So more intuitively, what we are doing here is this. So here you can see what I'm plotting here is the standardized return on bond A, okay, which was the triple B bond. And on the vertical axis is the standardized return for bond 2, which was the single A bond, right? And in the thresholds, we saw that if the return for the first bond is between minus 149 and 153, so between in this range here, the firm remains triple B. And for firm 2, if the return on assets is between minus 151 and 198, the firm remains A. So essentially, the joint probability is just the volume under this surface here, and this square with a surface on top of it. Okay. All right. So doing that, we can compute the joint probability. So this number here, 7969, is this number that you see here. The firm 1 stays triple B, and firm 2 stays single A. So this cell here, and we could compute all the other cells in a similar way, just changing the integration limits here in this expression for the corresponding thresholds. So basically now we have everything that we need to compute the credit value at risk of the portfolio. So we have essentially two important matrices, these 8x8 matrices. One is the table with the values of the portfolio, and the other is the corresponding probabilities. So we just basically need to, if we're doing this in Excel, we would just transform these matrices into two big columns and sort that big column from the lowest to the highest value. Okay, and then the procedure would be exactly like we did for one single obligor in the previous video. And so we could compute exactly the expected return in the same way, and then estimate the value at risk, again, exactly in the same way as we did for one single bond. Okay, and we would find that the credit value at risk would be 9.23%. Okay. So in reality, this method is not feasible for large portfolios. The reason is that this expression here, we cannot do this by hand. We have to do this numerically with a computer, but even a computer cannot do this for more than 5 or 10 bonds. In reality, bank portfolios have much more than 10 loans, right? They have hundreds of loans, and therefore we need some other solution. So for large portfolios, what we actually end up doing is the following. What we're going to do is to impose the correlations, we are going to use a factor model. So basically what we are trying to do here is to explain the return on each single firm as a function of some factors. And these factors are typically industry and country factors. So this small example shows how that factor structure actually imposes correlation between two firms. So suppose I have just two very small portfolios, just two firms. The first firm, Vivendi, loads up on two factors, T for telecommunications, L for leisure, with these loadings here. And then I have a second firm, General Motors, which is a car manufacturer, and so loads up on this car factor with a loading of 0.9. In addition, I estimate a correlation matrix between the three factors, T, L, and C, and it's this number here. So what we are doing here is just to show that these two equations and this correlation matrix between the factors are enough to impose correlation between the two firms, Vivendi and General Motors. So if I actually compute the correlation that comes from these expressions with this correlation matrix, I get a correlation of 0.072. Okay, so you can go through these steps here at home. This is just using the properties of variances and covariances and so on. Again, the point is to show that these structures impose correlation between the two firms. So the way we implement this in practice is the following, is through simulation. So we basically have these regressions that link each of the firms that we have in the portfolio to a small set of factors. Then we also have a correlation matrix for the factors. So how we simulate this? We generate random draws for the factors. This in turn generates returns for the firms. Having these returns for the firms, we compare these returns with the thresholds and find out what is the value of each firm in this first draw. We add up all the values and get the value for the portfolio, and then repeat. Draw again returns for the factors, compute the corresponding values of the firms, add up to get the value of the portfolio, and that was the value for scenario number 2, then repeat, and so on. Keep doing this 100,000 times or 1 million times or so on, and in the end what we have is a big column with values for the portfolio. And then from that column we compute the value at risk, exactly like we did for one single bond. Okay? We can talk more about this in class and go through the details in class if you have any questions. All right, so that's the end of it. There are some more details here in the end about other portfolio models. You can skim through this. We're not going to talk about this in class. The main point is that there are other alternatives that look somewhat different, but in the end, all these models, if done in a consistent way, give outputs that are basically consistent with each other. All right, thank you for watching. See you in class.